Welcome back to the Beginner's Guide to the Modern Theory of Polarization, a series of modules to help you understand how the electric polarization is defined, calculated and measured in bulk periodic solids. Brought to you by Schrödinger's Kittens Productions. Here we'll discuss the solutions to the exercise of Module 5. In Module 5, we were asked to think about problems that might arise when measuring the ferroelectric polarization using the Sawyer-Tower method that could lead to an underestimation or an overestimation of the true value. The first example we'll discuss is incomplete switching. Let's suppose that we start with a ferroelectric that's fully polarized in the up direction, so that its positively charged top surface is compensated by electrons in the electrode and its negatively charged bottom surface is compensated by holes. But when we apply an electric field in the down direction to switch the polarization, the switching process is incomplete, and instead of forming a uniformly down polarized sample, some domains of up polarization remain. This could happen, for example, if the coercive field required for switching is very high. Then the number of electrons that need to flow from the top surface to the bottom surface through the external circuit in order to compensate the new polarization is smaller than if the ferroelectric had switched completely. As a result, the polarization difference between the up and down polarized states is underestimated. In our second example, our ferroelectric material is leaky, in the sense that it is not robustly insulating, but contains free or weakly bound electrons or holes coming from point defects such as oxygen vacancies or donor atoms. This time, when the electric field is applied, the free electrons can flow through the external circuit, and if we interpret the number of electrons per unit area to be the size of the switched polarization, we will obviously get the wrong answer. In fact, there will even be a contribution in a non-polar material. These problems can be properly accounted for with appropriate circuitry, but it's important to be careful when making ferroelectric measurements. Now you're ready to move on to Module 6 in the series, where we'll discuss an example of how the surface charge associated with the polarization can lead to unexpected physics at the interface of two apparently non-polar materials, lanthanum aluminate and strontium titanate. Thanks for listening.